I think I may start today's lecture. Maybe next topic will be Riemann bilinear relations. By linear relations. First of all, assume that we have a compact Riemann surface of genus G. I think it's compact and regular. Gamma G. It's topologically a sphere with G handles. Here, G equals 3. First of all, we assumed that we have a system of cuts. Draw a system of cuts. We fix a point, A1, A2, A3, B1, B2, and B3. So we draw a system of 2G cuts. We start the cuts from the same point. If we then, after cutting the Riemann surface, along this line, we obtain for G gone. The following for G gone. And moreover, we can check the order of the lines. The order will be the following. A1. Of course, this system of cuts and the system of cycles is not unique. It's one of the possible choices, but of course, it's not the unique one. B1, A1 minus 1, A2, B2, A2 minus 1, A2 minus 1, A3, B3, A3 minus 1, B3 minus 1. It's one, of course, of the possible choices, but one of the possible. Okay. Then we have the following intersection numbers. Aj, and of course the corollary, Bi. Aj is minus delta Ij, of course. But it's corollary, I don't write it. The intersection form is symplectic, is skew-symmetric. That's it. J is 0. Such basis of cycles is called canonical. Of course, on the set of canonical bases, we have a very big group we have, I don't want to go into details, but you can see that group has a huge number of generators. It's a sufficiently big group acting on the basis of cycles. And then, if we have the following picture, we have the following theorem. I suggest the book Springer relation to Riemann surfaces. I recommend this book. Except I think the uniformization chapter was not written good. Uniformization chapter. But chapter about wild projections, existence, are well written, I think. First of all, what do we know? There is a following statement. First of all, do you know a basis of homology theory, some basic facts? You had some elements of topology, including homologies, or not? Okay. First of all, you know that cohomological group, first of all, we can calculate the fundamental group of the surface. Fundamental group is generated exactly by 2G generators, A1, AG, BG, and one relation. Now, how to see it? First of all, you see any path can be moved, homotopically moved to the boundary, and you obtain that a sequence of A and B. And there's only one relation. If you have the sequence, it can be shrink to a point. So it's fundamental group of the Riemann surface is a group with 2G generators and one relation. Of course, if you go to homologies, this we obtain free commutative group because these relations became trivial. It belongs to the commutator. Therefore, in homologies, you have basis of dimension 2G. So so you know the fact. I hope I don't want to explain it. Is it necessary to comment it or not?
Yes.
Okay. First of all, you have cohomological group. Of course, you know that how to calculate cohomologies for a cell complex. Or you don't have. Didn't. What you know? Did you have the RAM cohomologies or not?
Yes.
But some symplectic, yes or no? Only the RAM cohomologies. Okay, but first of all, you see that you have cell decomposition. You have one cell of dimension 2. 1 point. You have 1 point, 2G one-dimensional cells, and 1 two-dimensional cell. You see. So you have complex with the following set of generators. Okay, let me write. We have one-dimensional cell. It's a point. You see, of course, you have 4G points here, but they are all glued. In fact, it's 1 point on the Riemann surface. 2G one-dimensional cell. Dimensional cell. You have 2G one-dimensional cells. Exactly this, you see. And one two-dimensional cell. You have you see. Moreover, it means that we have 1 point, then we have 2G1 cycles, you see. And we see that the boundaries of all 1 cycles are equal to 0. Because boundary is 2 points, but it's the same point. Once is counted with plus, once is counted with minus. It's clear. Therefore, we have this complex, and we have 1-dimensional, 2-dimensional cell. Therefore, all operators, all differentials are 0. So we have Z. It means because we have only one-dimensional cell, 0-dimensional cell. We have 1 0-dimensional cell, and therefore, and it's not a boundary. Because all differentials, we have the following exact sequence 0. Is it okay or? No, it's not exact because it's not exact sequence. D square is equal to 0, but the kernel doesn't coincide. Yes, doesn't coincide with the image. Therefore, all differentials are 0. You see.
What is the differential that maps from two-dimensional cells to one-dimensional cells?
Okay, count. A1 minus 1, B1. No, but okay, what is the border of two-dimensional cell? You agree? Because it's A1, B1, minus A1, minus B1. A2, B2, minus A2, minus B2. You see? Sorry, is it okay? You see. No, but the boundary of the cell is the sum of the boundary cycles, you agree? In the boundary, any cycles counts twice. Once with positive orientation, once with negative. It means that the boundary is 0.
Okay.
You see. Because every cycle counts twice. A1 counts twice. B1 counts twice with opposite signs. A2, B2, and so on. Okay. You see, take any cycle here. You see that this point counts twice. Once with plus, once with minus. You agree? Therefore, all differentials are 0. You see? All differentials are 0. Because all differentials are 0, no factorization is. Of course, if you take homologies, you don't count the order. You understand? Homologies, it's not necessary. A, B. The order in which you have the intervals on the boundary is not essential in the homologies because you have commutative groups. If we calculate fundamental group, of course, the order is essential. But if you take the commutator, the order isn't essential. It doesn't require the order. Okay, so we have this. So we don't have any factorization here. Kernels coincide with the whole space. Image is 0. Therefore, it's H0, H1, H2. I agree. I see. Okay? Sorry. Okay. And but if you take in cohomologies also, all differentials are 0. Cohomologies coincide with homologies. Oh. So. As follows. There is a following theorem. I make a reference to the Springer book. I don't want to prove it's wild projection. I don't want to go into this part. So, but you can make some functional analysis. Maybe not too complicated, but there is the following projection procedure that you can introduce holomorphic differential. You can introduce harmonic function definition. Harmonic function satisfies the equation its definition. It's well defined. Harmonic function. Or equivalently, and then harmonic function can be written as a sum of holomorphic and anti-holomorphic, but okay. Locally, at least locally. Therefore, first of all, the statement is that if you calculate the RAM cohomologies, you may calculate in terms of harmonic differentials. So first of all, assume you have differential, omega. Exact differential. What's necessary and sufficient condition for a differential to be exact? You understand? Integrals over all cycles are 0. You understand? Mm-hmm. Differential is x if. Next remark. Okay, how to calculate the RAM cohomologies for this Riemann surface? Okay, maybe I'll recall it. How to calculate the RAM cohomologies. First of all, okay, the zero, H0 of gamma R, the RAM, is R, is the number of connected components. Do you remember its effect? Yes. 0. How to calculate H1? To calculate H1, first of all, remark that if a differential has all periods equal to 0, it's exact differential. Mm-hmm. It's if you have a closed differential. So if you have omega, one form such that d omega is equal to 0, and 0. Then we can take primitive of the form. It will be a single-valued function. You understand it? It's a single-valued function. Differential is a differential function if and only if a closed differential. You have closed differential. D omega is equal to 0. Necessarily sufficient that integral over all cycles are equal to 0, you agree? Because if you have a differential function, the integrals over all cycles are equal to 0. And vice versa. If integrals over all cycles are equal to 0, then you can take the primitive and it will be single-valued. Therefore, it's necessarily a sufficient condition. So for the dim is not greater than the number of cycles. And you see that if you have any cycle could be deformed to a cycle along the boundary. Therefore, it's a sum of basic cycles, and they're independent. Therefore, dimension, so we have criterion. Differential is closed if and only if all periods are equal to 0. Now, can I draw it here? Let me draw it again. Do you see what I'm drawing here? First of all, you can slightly modify the cycles in this moment. B1 B2 Miss oh sorry B1 I'm sorry, this direction B1 B2 and B3. Now, we can introduce the following differentials, for example. For example, consider such a belt near the cycle B1. Consider a belt. On the belt, you can introduce coordinates, draw the belt. It's near the cycle B1. Cycle B1 goes along this belt. B1. Then introduce the coordinates. Example. R and phi and phi. for example, alpha r and phi. So for, and let's define the following differential. Consider a function of r, such function of r, 0, 1, f of r. You know how to construct regular functions with following properties. So it's 1, it's 0, and it's smooth. Its differential is 0 as the boundaries. So we can continue the differential to the whole Riemann surfaces. Assume that it's 0 everywhere outside the belt. Understand it? Differential is the following. Is here is this one. We have function q of r, dq of r. That's it. R is 0 here, 1 here, and it's on the belt is, and differential vanishes on the boundary. No, I'm sorry. This differential, you see, we have such differential. What is the problem? First of all, it's globally defined. Why? It vanishes at the boundary of the belt, therefore it vanishes you can continue everywhere by assuming that it's 0. Sorry, I'm sorry, the opposite direction. 0, 1. First of all, we agree. Because A1 goes this way. A1 goes this way, you see. The cycle A1 goes this way. Okay? So integral over A1 is the difference of the function. That is clear. Okay, let me repeat it. So let me redraw the belt. B1 and we have A1. A1. Everywhere else, the differential is equal to 0. The integral of A1 is the value of function q here minus function q here. Q is equal 1 here, is 0 here. Therefore, integral of A1 of omega is equal to 1. Okay? Integral of B1 is equal to 0, and all integrals over all other cycles are equal to 0. I agree.
Omega equal dqr.
dqr, yes. So such differential, integral over A1 is equal to 1, integrals over any other is equal to 0. Agree. It's clear, because over B1 is equal to 0, and everywhere else it's 0. All other integrals are equal to 0. Then we can repeat the same procedure, but instead of taking this belt, consider this belt. You see. And we repeat the same procedure. You obtain differential such integral of B1 is equal to 1. All other integrals are equal to 0. And they are all differentials locally of a function. Therefore, they are closed. see. Therefore, we constructed a set of closed differentials consider 2G differentials. You see. We consider 2G differentials. You see. To G closed differentials.
Omega prime
Is it by the second belt. Omega is constructed using the first belt, omega prime using the second belt. You see. So we construct 2G differentials. Therefore, and this is that any other closed differentials is homotopic to the sum of, homological to the sum of such, because we, by subtracting the differentials, we can make the integrals over all cycles equal to 0. You understand? We subtract sum of such linear combination of differentials, and the integral over any cycle is equal to 0. Therefore, it's a exact differential. So we prove this one. You understand? And now what remains?
So we took this 2G differential form.
Yes, we constructed these 2G
differential forms, and
any other closed differential form is cohomological. Is of such these forms.
So these forms are not exact.
Yes.
But all others can be constructed as.
We can any other closed form is a linear combination of this form plus the differential of a function.
Therefore, we have this. Okay.
And how? Okay, we have to prove the following statement. Do I have to prove it or not that if you have a two form such that integral over gamma is equal to 0, then this form is exact. Okay, let me. Okay, assume that you have a local statement. You have one form in a plane. One form with finite support. Two forms, sorry. Omega is dx dy. We have two forms. How to construct? Okay, we can try to construct a form which is a. Okay, let's prove the following statement. Assume that omega d omega, if and only if. So, sorry, okay, for omega 2, lemma. is compact support if so the form omega 2 is a differential of a form with compact support if and only if integral of omega 2 is equal to 0 in one direction. Assume that omega 1 has compact support. You agree? Then we calculate this integral of omega 1. Using Stokes theorem, integral over this contour of omega 1 okay, gamma you agree. D. D is this area inside this contour. You see. In one direction, if omega 1 has compact support, then we apply the Stokes formula, and we see that integral of omega 2 is 0. Okay? Now, let's prove it into the opposite direction. How to prove it into the opposite direction? Assume that we have such form. First of all, let's try to construct omega 1. The first idea is the following. Assume that the support is located in the area. Okay. So we have some constant C. And the support of the form is located in the area greater than C. Then we can introduce the following. Try to choose the form omega 1 tilde will be of C by X You agree. Let's define such a form. Such a form.
This definition make in one map.
Sorry. No, okay. This definition. Okay, you can calculate differential. The differential is correct.
Why this definition is correct?
Sorry. No, we can write such a formula.
Omega 1 tilde is formed in surface.
No, in the plane. In the plane.
Plane?
Locally.
Okay.
We make calculations in the plane. This moment. You proven lemma for the plane. For the plane. Of course, you can calculate. It's exactly. I agree. Okay. So this is, but what's wrong? Because this form is good, but with one exception. It's non-zero in this area, you agree? But, okay, first of all, we see that we can add to omega 1 tilde a differential of any function, you agree? You agree? You can add. Because we have d squared is equal to 0, then we can replace omega 1 dh. You agree? Because it doesn't affect the differential of. Now, let's choose the following. C2. Okay, let's note it by C2. A couple of constants introduced. Let's define a function. Okay, first of all, p of x. Let's define such a smooth function, p of x. And then, of course, let's introduce the following notations. Okay, may I remove this figure? Let me introduce the following notations. Can I do it? Okay, let me denote this d1, and this will be denoted d2. So the co-support is inside the square. Let me define h, omega. Let me write formula. Mu of x Can I do this way? Yes, you understand what I have done. Now, let's look to the formula first of all. Let's see. In the area before d1, everything is equals to 0, you agree. Here, omega 1 is equal to 0, you agree. And what happens here? Here, you agree. Here, it's in this. It's this interval. No, sorry. I did a mistake. Minus differential of this object. You see. What happens? Let's calculate d omega 0. In the area for what happens? First of all, you see for x smaller than C1 is equal to 0 by construction. So, what is a dangerous place? You see, let's have a look. What the place? Wait. Okay, let's look to the diagram. Here is 0, but only we have this dangerous area. You understand? You see. Everywhere except this area, the form is 0. You agree? Isn't it? Because here f capital, here the integral is, okay, above this area, this integral is constant, you agree? This integral, or this integral, is constant above this line, you agree? Is constant.
Sorry, f small.
The original.
Okay.
Because what happens if, yes, okay, let's analyze. Okay, maybe we have to analyze. First of all, let's assume where omega 1 is non-zero in this area, you see, omega 1 tilde. You see. P of x is non-zero. You see, first of all, P of x is here, P of x is 0. Therefore, in this area, everything is good. You see, in this area. Yes. First of all, intersection. You see this? First of all, you see. You have this statement. If x is smaller than C2, intersection of support of omega 1 with this area is compact. Because support this set, okay, let's denote it, for example, D1, this area. D1, okay. Because I agree. Because suppose this object, area D1, lies inside the square. Before it's compact, you see. Now, what happens here? If first of all, second state, if you see, because here omega 1 is 0. Why? Here P is identically 1, you see, P of x. Therefore, this in this area, differential of this guy is exactly f tilde of y dy, you understand? So, and omega 1 is, because in this area, dy and this differential, you see. So, in this area, everything is good. Things with a correction. Therefore, which R remains? Okay. Third. I'm sorry. Area. In this area, you see, what happens in this area? By definition, in this area is 0, and you see, it's okay. So, the only area which we may have problems is this one. It's the only problem. The only area is this one. So the only dangerous area, well, the dangerous area is this area is the most important. But what happens in this area? This area, this is that omega 1 tilde is 0. Here, what in this area? It's 0, and omega is minus times integral we agree? You have this formula. Therefore, equals to 0 if and only if this is equal to 0. Yeah. Okay? So is it clear? Sorry. Therefore, for the form we constructed, so what we obtain? Compact. If our conclusion is that if A1 by T2 is equal to 0, you see. Necessary and sufficient condition to obtain compact support in this construction. Integral of y of f capital is equal to 0. But it's exactly, but this integral is exactly integral, double integral of omega 2 over the plane. But it's exactly. So we proved that our construction provides a compact support form if and only if the integral is 0. So it's not insufficient. Okay? We proved the lemma. I don't know, by the way, I don't know. I never saw. It should be somewhere, but I don't know where to find this construction. But it's very simple. You agree? Because it's absolutely explicit, I prefer. You agree? This is it. This is calculation. What we proved that the form is closed if and only if in the class of compact support forms. It's closed if and only if the integral is equal to 0. Now, let me return to our Riemann surface. So, you see, we have a Riemann surface graph. First of all, we can represent any form as sum of forms with compact support. You see. Then we can do the following. We have form. Such that all forms have compact support. You agree? Then we can do the following. Choose one. Choose some neighborhood. And if you have, okay, we have another. We have two form area. Then we can, on the Riemann surface, we can, you understand, we have two areas, we can draw some slices. You see. And then we can do the following. We can have we can form here, so omega k. Then we do the following. We can construct always some form with compact support and non-zero integral. You agree? It's easy to construct explicitly some form. No, it's not a problem to write a function. You remember, I think on calculus you explained how to construct a smooth function which vanishes everywhere except some interval. Yes. Of course, without loss of generality, we assume that integral of this function is 1. You agree? Remember?
Yes, like head.
Some heads, smooth heads. You remember? You can have smooth heads. For example, P of x. P of x, for example. Then we write form. In some local coordinates. You can define such form. It has compact support and integral equal to 0. Then we add such form here, subtract form here. And after it, integral here equals to 0. We replace any form omega k by a form which now has support in this area, but it's okay. And this integral equals to 0. Then we apply our lemma, and we can concentrate all the integral in one small area. You agree? yes, we do the following. We have two areas, for example, U1, UK. We have form omega k here. Let's denote omega 0. And we replace. We here to the area add what we do this subtraction of this area, and then we add here the form. And we here subtract this, and we add this form. We remain in the same cohomology class. Because in this area, the form has the additional form has zero integral. So it has primitive with complex support. You see. Therefore, if we subtract here, add here, we remain the same cohomology class. You agree? Therefore, we can concentrate the whole integral at one area. All other forms are cohomological to zero due to our lemma. So we have everything concentrated in one area. If integral is zero, the primitive also has complex support. If not, so the only obstacle is the integral. So is it clear? Yes. Therefore, using this lemma, we prove that we proved it. So we calculate the Riemann cohomologies for the Riemann surface. Now we can define the star operator. Let me define it. Let me define the following way. Now, next, lemma theorem from Springer. There is the following. One can construct the projection operator from one forms. The following projection operator from closed one forms to harmonic one forms. With the following property. It keeps integrals over periods. Therefore, you can have exactly 2G harmonic forms. 2G harmonic forms. Now, let's introduce the following operator. Harmonic form is a differential of harmonic function. And locally was new harmonic form. Form is harmonic, omega. You agree? Locally, it's local statement, local representation. Up to constant, but okay, it's local representation. Harmonic form with harmonic finally has a form representation. Of course, you see that form is automatically closed, a closed form. Now, let's introduce the following operator, star. Use the following formula. And this operator acts on harmonic forms. On the harmonic forms, it has to, moreover, we see star square is -1. Is -1. Consider that you have 2G-dimensional space of harmonic forms, you see. And operator star acts on the space. The eigenvalues of the operators are I and -I. Understand? If we have such operators, the square of operators -1, that eigenvalues are either I or -y. Understand it? It's therefore. So we have, this space has dim 2G. This operator star acts on this space, on harmonic forms. Then you'll see that we have dim G. And of course, we have complex conjugation of the forms. And maps eigenvalues I to eigenvalues -I. So we have two spaces. V. So we have V is the eigenvalue with the eigenvalue -I, it's the eigenvalue is +I. Eigenspace with +I with -I. Two eigenspaces. They have the same dimension. So dimensions are equal to G. Equal to G. You see. And V1 are exactly holomorphic forms. The forms from V1 are holomorphic. So you see, locally, of course. Therefore, it's holomorphic. Therefore, the space of holomorphic forms is G-dimensional. Maybe I decided to explain it, because I had the impression that at the previous lecture it was not motivated. Yeah, I understand. The space, the complex dimension of the space of holomorphic form is 1/2 of the space of dimension of harmonic forms. But harmonic forms represents cohomologies. And cohomologies is 2G dimensional. Therefore, the space of holomorphic forms has dimension G, 1/2. Because we have harmonic forms are holomorphic forms plus anti-holomorphic forms. Maybe I decided to explain it in this way. Okay. Now, I don't want to repeat, but using similar argument, one can prove that. I don't want, because assume, so, theorem from Springer. Theorem from book, Springer book. First of all, dimension of space of holomorphic one forms equals to the genus of the Riemann surface. First statement. Second statement. The matrix assume that we have some basis, omega 1, tilde, omega, еще tilde, some basis. Then AKL in the statement what is essential. We do not take integrals over all cycles. We choose 1/2 of the cycles, but special 1/2. We can tell that we choose some Lagrangian subspace. Understand that intersection form on the cycles A1, AG equals to 0. Therefore, in some sense, they generate Lagrangian subspace. You understand that? Assume that you have a space R, for example, R2G with symplectic form. This is skew-symmetric. You have some skew-symmetric scalar product on tangent vectors. Oh, assume that you have RG two dimensions of UV. Some skew-symmetric scalar product. Then a space V in R2G if first is G first of all, this first property that its dimension 1/2 maximum, and the second, the restriction of the form completely vanishes. Because in mechanics, if you consider coordinates, they form a Lagrangian subspace. Or you consider momenta, they form a Lagrangian subspace, you understand? But not only. So Lagrangian subspace means a subspace of dimension. If you have dimension greater than 1/2, a non-degenerate symmetric form could not vanish, you understand? The highest possible subspace on which the skew-symmetric form identically vanishes is 1/2 of the whole dimension. You know it. If you have skew-symmetric matrix, then what are the space on which the highest possible dimension of the space on which the form identically vanishes? You understand? The highest possible dimension in 1/2 of the full dimension. You have symplectic form, symmetric form. Okay, may consider an example. Assume you have typical space, for instance, P1, Pn, P1, Qn. Okay. Is 0. Remember the standard Poisson structure. You recognize standard Poisson structure. So, what are the typical Lagrangian subspaces? We have, for example, typical. It's Lagrangian subspace generated by all pi. Agree? So Lagrangian subspace. But once we have such Lagrangian space P1, it's also Lagrangian, you agree?
Why also Lagrangian?
No, because, okay, let's consider, for example, equal to R6. R6. First of all, the Poisson brackets of P1, P2, P3 is equal to 0. You agree?
Yes.
The Poisson brackets of any functions from this subspace are equal to 0 from unique. But if you consider all Poisson brackets here are also 0, you agree?
How to find Poisson brackets in 3?
No. I think not Poisson brackets. The subspace. Consider the space P1, Q2, P3. You have 3 Poisson brackets. P1, P3 is 0. P1, Q2 is 0. Q2, P3 is 0. So it's Lagrangian. Okay?
Okay, Lagrangian subspace.
Yes.
Any vectors
Has 0
any
bracket.
pairs,
Here, any pair has 0 Poisson bracket, yes. No, by the way, it's very important in all classical mechanics and quantum mechanics, Lagrangian subspaces.
okay.
You recognize? So easy. So in this case, the cycles A form a Lagrangian subspace here. You understand? Cycles A. They form a Lagrangian subspace because the intersection of them is equal to 0. So in this theorem, it's important that we integrate over cycles from some Lagrangian subspace. You understand this here?
A cycles is Lagrangian subspace.
Yeah, yes, B cycles form Lagrangian subspace. We can take, for example, Lagrangian subspace A1, B2, A3.
Yes.
It should be any Lagrangian subspace, but Lagrangian. You could not take basis A1, B1, A3. It's not Lagrangian.
Yes.
Here is any Lagrangian subspace, then it's non-zero. Understand?
This easy?
Sorry.
This easy?
I can prove it, but not maybe tomorrow.
Okay.
But there is some theorem from Springer book. Maybe I can prove part of it, but not all. But nevertheless. It's necessary to prove it. I can prove it, but it requires a proof. No, it's not trivial. All the statements are non-trivial. I tried to explain the first statement, but without. I omitted the part about projection to harmonic subspace. You understand? I omitted this part.
Okay.
So it's some functional analysis. So the second statement, therefore, you can choose canonical basis. In some school, in some textbooks, they use this normalization. In some textbooks, they use this normalization. Okay. But nevertheless, you can choose such a basis. So you have Riemann surface with a fixed collection of A and B cycles. You can fix a canonical basis. But canonical basis depends not only on Riemann surface, but also depends on the selected basis of cycles. But cycles are canonical. They have this intersection number. It seems that. Okay, 0. You remember. We always consider the formal object, the Riemann surface, with a fixed basis of cycles. You understand? Then if you have a fixed basis of cycles, you have a corresponding canonical basis of holomorphic differentials. You see? Then, next statement. Okay, I want to make reference to the Springer book. It's impossible to include everything. Then, third, assume that we have a let's some point P in gamma, Riemann surface, and we have a local coordinate. Define an arbitrary singularity with zero residue. We fix a point, and we define arbitrary singularity, but with zero residue. You don't have C minus 1 term, you see. Then, there exists a unique differential omega. Okay, let's note omega 0. It's some local series, some local formula, it's some local, such that, first, so first of all, omega is regular outside this point. Near this point, it has this expansion plus something plus some regular term. And the third statement now, first of all, you understand that you have differential. You can add arbitrary combination of holomorphic differentials. You agree, to omega. And if you assume that all A periods are 0, then we kill this degree of freedom. It's clear that if you impose this condition, then what is the difference of two such differentials? It's regular, and it has 0 A periods. Therefore, it's exact. You understand? It's holomorphic. So you need to have two such differentials. The difference will be regular anywhere, holomorphic. Therefore, it has 0 A periods. Therefore, it's identically 0. Therefore, it's unique. So non-trivial is existence. And the fourth statement is that assume that we have 2 points, P1, P2. You're right. And we can the differential omega equals to Do they have any pair of points, P1, P2? Then there exists unique differential such that it has first order pole with residue 1 at P1. It has a first order pole with residue minus 1 at P2. And okay, the integrals. Therefore, roughly speaking, we can do the following. We can write arbitrary set of singularities with only one constraint. The sum of residues equals to 0. Then there exists unique differential with prescribed set of singularities with 0 A periods and holomorphic everywhere outside these points. The theorem from Springer book.